the second lecture of Professor Karel Dekimpe. He will continue his course on Post Lie algebra structure. So please, Karel.
Okay, thank you very much. So indeed, I will continue the course on Post Lie algebra structures. So I think it's good to recall a little bit some stuff. So I started with the definition of Post Lie algebra. So this was V, vector space equipped with curly brackets and a dot product, with some conditions. And then the first thing I showed was that there was a second associated bracket, which I denoted by square brackets, which is also a Lie bracket. And then I more or less transformed the definition of a Post Lie algebra to a Post Lie algebra structure on a pair of Lie algebras, G and N, with the same underlying vector space. So the G will always have square brackets, the N will always have curly brackets. And then we have three conditions. So first of all, the product relates to two brackets, and then let's say the left multiplication should be an morphism from G to the derivations of N. So here we see that's derivations of N, that multiplications, and here we see it's a Lie algebra morphism of G to these derivations. So this is the definition of a Post Lie algebra. Once again, I will come back to it later, so you don't have to remember it quite deeply. I then showed what happens in two special cases, namely when the Lie algebra N is abelian, then this more or less reduced these two conditions. So this one disappears, the bottom one too, to these two conditions, where actually you can replace the second one also by saying that the associator of x, y, z should be the same as the associator of y, x, z. And so this is the reason why these structures are called left-symmetric structures. Yeah. Then I did the converse thing. So I said what happens if G is abelian, and then it turned out that again you have the curly brackets which are related by the product, and then we got up with the situation that left multiplications and right multiplications have to commute, and so this is a bi-commutative algebra, or what me and my colleague would have been calling LR structures coming from this left and right multiplications that commute. And so this was the point that I stopped yesterday, but actually maybe it's good to just have a look what happens if both N and G are abelian. So before I continue, just for an easy warm up, what if both, this bracket is 0 for all x and y, and this bracket is 0 for all x and y. So in case both N and G are abelian. So what happens in this case is that, of course, we have this condition still, but this bracket vanishes and becomes 0. So we see that the product has to be commutative, and left and right multiplications have to commute also with each other. We can rewrite this a little bit. So we have that x, y, z. So the product has to be commutative. So this should be the same as y, z, x, because I just replace it. I also know that right multiplications have to commute. So I can interchange x and z over here. So I know that in this situation this should hold, and then the product has to be commutative over here. So I change the order of these two. And so what I do get is that my algebra is just associative in this setting. So if both N and G are abelian, I do get the associative algebra and the commutative algebra. So it has to be commutative plus associative. And actually the converse also holds. If you have a commutative and associative product, then you have a Post Lie algebra product on the pair Gn when both G and N are abelian. So this is a small exercise to show what happens in this special case. So what I'm going to do for most of the time today is to switch totally the point of view, and instead of looking at, let's say, mainly algebras, I'm going to approach these structures using geometry. And this is actually the reason why I came into contact with these structures. So Post Lie algebra was originally defined by Bruno Valette in 2007, in a context totally out of my expertise. And I encountered these Post Lie algebra structures during a geometric setting. And I want to explain today a little bit this geometric setting because this is the motivation for me for studying those structures. And secondly, they will also give a new interpretation of these Post Lie algebra structures. So once more, new way of seeing what the Post Lie structure is. So if you cannot follow everything because you're more into algebra and less into geometry, don't worry. We will not really need it, and you will probably be able to follow more or less what is going on. Okay, so the third point of my course. So the first point was the definition. The second point was the special case when n and or g are abelian. And the third point, let's say this is the geometric motivation for studying those structures. And before I start this geometric motivation, let me recall a few things also to fix with the notation. So first of all, what I will need is the notion of a summative product of two Lie algebras. So we start with a Lie algebra G and a Lie algebra N, and we consider a Lie algebra morphism from the Lie algebra G to the derivations of N. And using this, we can build new Lie algebra, the similar product of N and G. And if you define the re-bracket, so I have an element xy component in N, component in G, another such an element. Then the Lie bracket will again be a pair, and the second component, this is just the bracket in the G part. The first component, well, I always use curly brackets for N, so I will keep using this notation. So this is take the curly bracket of the x's and then use this map row. Maybe I need a little bit more space. So plus row of x1 acting on y2 minus row of x2 acting on y1, and then I have this bracket. So this is how you can define new Lie algebra having such a map from G to the derivations of N. So it's an easy exercise to show that this is indeed new Lie algebra. And one example that we always can use, and which I will use today, is you can just take G to be equal to the set of derivations of N. And then as a map, you take the identity over here. And then the bracket x1, let's say d1, because I'm taking derivation, I will use the d, x2, d2. Then it's just the bracket of x1, x2 plus d1 on x2. Oh, this should be the other way around. It's the y's who act on the x's. Row 1 on x2 minus row 2 on x1. So this is d1 on x2 minus d2 on x1. And then the bracket of the derivations, which is of course just d1 d2 minus d2 d1. Okay. So this is for me today, the Lie algebra that I will, the semi-direct product that I will encounter, but this is a general construction. So this is the first thing you should know. And the second thing you should know a little bit is, well, I hope that you all know that the algebras and Lie groups are related to each other. So if you have a Lie group G, there is an associated Lie algebra G, small g, and there is also a map from the Lie algebra to the Lie group, which is called the exponential map. And if you have a morphism of Lie groups, so this is a continuous, well, let me call this phi, continuous morphism from G to H, and then you have the Lie algebra H, small h of the Lie group. Then, if you look at the differential of this map, you get the morphism of Lie algebras over here, and this diagram is commutative. And actually, if G and H are both connected and simply connected, you can also go from morphism over here to morphism on the Lie group level. And this is often helpful because morphisms of groups are, well, difficult, while morphisms of Lie algebras, these are just linear maps preserving the Lie brackets. Yeah, this is always easier to study. And so this is a very good tool when you're dealing with Lie groups. So these are the two things I will need in my, let's say, explanation about the geometric motivation for studying post Lie algebras. So let me now start with the story. So the story starts with the affine group of Rn. So I will be using the affine group of Rn. So this is the group of invertible affine maps of Rn. So such a map, what does it do? So such a map goes from Rn to Rm and takes, let's say, an element, let me denote it by a vector x, and it sends that to, let's say, the translation part plus a linear map acting on x. So this A is the translation part, belongs to Rn. And the big A is an invertible matrix because I'm interested in invertible affine maps. If you look at all affine maps, this is just a square matrix. Oh, sorry, G and R. And so such an affine map, we can denote it by small a and big A. Yeah. And because I'm a little bit lazy, I will no longer write these arrows above the vectors, but you know that I mean that this is a vector. So elements of the affine group are tuples, an element of Rn, and an element which is an invertible matrix. Now, if we multiply two such elements, so this should be the composition of two maps. But if you see what happens on the element x, so this is AA applied to B plus BX. And so this is the affine map, translation part plus rotation part, well, linear part working on X. So you see that you get an affine map with this translation part and this A times B linear part. So this is what the product looks like applied to X. So the product of two elements is this element. And this group, this structure actually corresponds also to a semidirect product, but then on the group level. So the affine group of Rn can be written also as a semidirect product, Rn semidirect G and R. So we have translation parts and rotation parts, and the group structure is such that it becomes a semidirect product in group theory. Okay. This is a Lie group again, and it has a Lie algebra, which I also write as F Rn, but then it's small letters. And as a Lie algebra, this is a similar product of the Lie algebra Rn, by which I mean the abelian Lie algebra, so brackets have 0. Yeah. And the derivations of this Lie algebra are all possible linear maps. So this is just G and R. So the Lie algebra of this Lie group is this Lie algebra. Okay. And so elements over here are also elements of the form AA. Okay. But now this matrix does not have to be invertible anymore. We have BB, and if we look at the bracket, what we get by definition is the bracket of A and B, which is 0 in Rn, plus this derivation, linear map, acting on B, minus this derivation acting on A, and then the Lie bracket of A and B, which is AB minus BA. So this is how this Lie algebra is defined and looks like. Now, why did I get interested in this affine group? Well, this has all to do with the question of John Milner. Dating back to 1977, so long time ago. And actually, he formulated two questions, one on the level of discrete groups and one on the level of Lie groups. And I will consider the one on Lie groups for today. So the question on Lie groups is the following. This question was, which Lie groups G admit a simply transitive affine action on Rn. So and actually he formulated it as a question, but his idea was that probably the class of groups admitting such an action was the class of simply connected solvable Lie groups. And let me go a little bit into more detail now. So what is the simply transitive affine action of such a Lie group? So this means that we have morphism of Lie groups, rho going from the group to the affine group in such a way. So simply transitive action is a morphism of this form. This is simply transitive action. If and only if for any AB in Rn, there exists exactly one G. So for me, this symbol means there exists exactly one G in my group G, such that if I look at the affine map rho of G and I apply it to A, that this should be equal to B. So this means the action is transitive. Yeah, or there is only one orbit. And we can go from one element to another element by exactly applying one G. So this is simply transitive. Okay. We can also say this a little bit another way. So for example, you can say if you look at the evaluation map at 0, F0, going from G to Rn, mapping G to rho of G applied to 0, to the 0 vector. Yeah, well, we should reach every element of Rn. So take A equal to 0. We should reach every element in Rn, and exactly once. So this should be a bijective map. And since we are working in the setting of Lie groups, this should be a diffeomorphism. Okay, and at the time that John Milner posed this question, which Lie groups admit a simply transitive affine action, then it was already clear that if you have such a simply transitive affine action, your group has to be solvable. Because the fact that your group is mapped into the affine group, and the affine group is a linear group, and one knows that linear Lie groups which are diffeomorphic to Rn, they have to be solvable. Okay. So it was already known that if you have this, certainly G is solvable. And actually, John Nunner asked the converse question: is it true that if you take simply connected and connected solvable Lie group, does it admit such a simply transitive affine action? So this was his main question. Okay, people have been studying this question for several decades, and one successful way to study this question was to translate this question to the Lie algebra level. And so let me explain a little bit how this was done. So I think I will erase this part. So suppose now that rho from G to the affine group is such a simply transitive action. So what I get is I get G going to the affine group of Rn, which can be written as a semi-direct product. I know this is rho. I know that G has a Lie algebra, and we have a connection by the exponential map. We also know that we have over here the differential going into affine map, which is Rn semi-direct small gn R. Also an exponential map over here. And now, what do we know? Well, we know that the action is simply transitive. Okay. So we know such a G is mapped into a pair. Let me call this translation part of G, the linear part of G. And we know that if we look at rho G applied to 0, yeah, and we let G vary over the whole group G, then we get the whole of Rn exactly once. And this evaluation map is, of course, applying AG, small ag, big AG to A, which is AG plus AG applied to 0. This is just the translation part. Okay. So we know that rho satisfies the fact that if you map G onto this part, that the map from G to Rn mapping G to small ag, that this is a diffeomorphism. So we have a morphism over here in such a way that if you restrict to the first factor, you get a diffeomorphism onto Rn. Okay, and then some work had to be done. Yeah, it's not at all trivial, but this implies that if you look at the map D rho, this sends an element x to also an element in Rn. Let me say T of x, T for translation part, and well, let me say L of x for the linear part of x. Yeah, so we get a map of this form, and with some work, one could show that also the map Tx going from the Lie algebra G to Rn, yeah, sending x to T of x is 1-to-1, so it's bijective. So if you have a semi-transitive action of your Lie group, then you have a morphism dg from G to the affine group, to the affine Lie algebra, sending x to such a tuple in such a way that restricting to the first factor is a bijective map. Now, being bijective for this map, yeah, well, let's say T for this map E, being bijective actually means that T is an isomorphism of vector spaces. Okay. So as vector spaces, G is isomorphic to Rn as vector spaces, and so we can identify them with each other. So we can say that G is actually Rn with some bracket, with a V bracket. And of course, we will make the identification in such a way that we have T as the identity map. So we choose a basis of G, using map T, so that actually, if you look at coordinates, this is just the identity map. So we can conclude that such a map G rho is in fact a map, after identifying G with Rn in a good way, to the affine the algebra mapping small x to small x comma linear part. And so I use T to identify the elements. So once again, if we have the semi-transitive action over here, we have the algebra morphism of this form. After identifying G with Rn, we should have this kind of thing. And now what does it mean to have this kind of algebra morphism? So we will simply write down what it means for D rho to be the algebra morphism. So this should be equal to the image of the bracket, should be the bracket of the images. So this is a different definition now, more or less. So you have the bracket and you have the part of the bracket. And remember, this is a sum-and-direct product algebra. So first the brackets of the elements, which is 0 because we are looking at abelian. Then Lx applied to y minus Ly applied to x, and then the V bracket of the map Lx. And now what we see is the following. Well, define a product dot on G or Rn. This is just the same vector space by x dot y equal to Lx of y. This is of course the reason that I chose L, not only because it's linear, but also because it's left multiplication. And then it satisfies the following things. First of all, this part has to be equal to this part. So we do have that xy equals x dot y minus y dot x. And secondly, this guy has to be equal to this guy. Or if you apply left multiplication to general element z, we get that xy times z has to be the same as x times y times z minus y times x times z. And if you now look at these two conditions, what we do get is exactly the two conditions I wrote more or less over here at the beginning of my class of today. And this says that dot is a left-symmetric structure on the algebra G. So, conclusion: if the Lie group satisfies, has a semi-transitive affine action, then its corresponding Lie algebra should admit left-symmetric structure. And actually, more is known. And there is also the concept of a complete left-symmetric structure. And complete means that if you look at right multiplications, these maps should be nilpotent maps. And then one can even show that the Lie group G admits a simple transitive action, even only if it admits what is called such a complete left-symmetric structure. But don't worry too much about this completeness. And so you see that left-symmetric structures really appear in a more or less natural way when studying these simple transitive affine actions. And using this correspondence, one was finally able to give an answer to Milner's question, and the answer was negative. So in 1995, Yves Benoit published a paper, but the preprint was already available 3 years before, in which he shows that there exists a connected and simply connected nilpotent Lie group not admitting a simply transitive affine action. So, as you might know, nilpotent is even closer to within than the general notion of solvability. I will come back to the exact definitions for Lie algebras later. So this certainly shows that not all solvable Lie groups admit such an affine action. Okay? And the example he gave was 11-dimensional, and the nilpotency class was of class 10. Okay? And the way to prove this was actually really using the fact that you can translate the group problem to Lie algebra problem and then exploiting this part to get to conditions showing you that you do not get a complete left symmetric structure on the Lie algebra of this nilpotent Lie group. And actually, in the same year, my colleague from Vienna, Dietrich Burger, and his supervisor at the moment, Fritz Grunewald, generalized this example to a whole family of examples, and they could also lower the dimension and the nilpotency class by 1. Okay, so this is how left symmetric structures pop up in the geometric setting. I am giving a course on post Lie algebra structures, and how did they pop up? Well, the moment we knew that affine groups are, let's say, not big enough to contain all solvable groups as groups of semi-transitive affine actions, we started to look for alternatives. Are there better ways to see this? So what I did was, well, instead of looking at the summative product Rn with G and R, which is the affine group of Rn, I replaced this Rn, which is an abelian Lie group, by a group which is as close as possible to this one, namely a nilpotent Lie group. So I took an N, a simply connected nilpotent Lie group. You can consider anyone you like. And I looked at his affine, its affine group. And its affine group is defined as follows. You take the summative product of the group with its automorphism group as Lie group. Okay? And now you should see that indeed G and R, this is the group of automorphisms of Rn, which are continuous. So the automorphisms of Rn as an abelian Lie group. Okay? And then you can define all the same things as before. So you have elements, let's say translation part A and automorphism alpha acting on an element of the Lie group. And so this is small a, this was big A, but I prefer talking about automorphisms to write alpha. Okay. This should be the translation part plus the linear part applied to n. Of course, I do not have a plus. This is just the multiplication in the group. And for the rest, you can ask directly the same question as Milner's question. Namely, which Lie groups G admit a simply transitive action. So rho going from G, the affine group of N. And again, it's easy, well, it's not easy, but it's well known to show that if you have such a simply transitive affine nil-affine action, what I call, such a simply transitive action on a nilpotent Lie group, then certainly he must be solvable. The question was just like for the question of number, does the converse hold? If you have a solvable Lie group, can you find some nilpotent Lie group and a simply transitive action like this? And again, I translated the same in the same way the problem onto the algebra level. So let me use exactly the same scheme. So suppose I have such a simply transitive affine action. Then I have again the diagram with the Lie algebra, and the Lie algebra associated to this group, which is a Lie group again, is really n semi-direct the derivations of n. Yeah? And I also have such an exponential map over here. And now, when rho is simply transitive, so this means if you look at rho of g and we write it as small a of g, alpha of g, and we apply rho of g onto the identity element of n that we denote this by e or by 1. So this is ag alpha g applied to the identity element. So this is the identity element. So this is again small a of g. Okay. So this means that if I map here g to a of g alpha of g, that the map sending g to small a of g has to be a diffeomorphism. And again, with some work, you can show, and now I have to be honest, under certain conditions, and it would lead us too far to go into detail, but under some conditions, I can show that the map sending x to the corresponding thing over here. Let me do it again by t of x, L of x. Where now L of x is a derivation of n, and t of x is an element of the vector space G. That again, the map T going from G to n, and then x to p of x is an isomorphism of vector spaces. Okay, and now we can do more or less the same thing. Using this isomorphism, we can identify the Lie algebra G and N. So we can assume that, well, they're certain that they have the same underlying vector space. And then I can write again as t of x as x. Just, There are some technicalities, but let's not go into details about this. So I can assume that the map 0 goes from G to N semi-direct derivations of N, and sends a small x to x L of x, using the T as the identification map. And now again, let me express what it means for B rho to be a Lie algebra morphism. So I have B rho of xy should be the Lie bracket here. So this is of course just like a few minutes ago, x comma L of x for this bracket, and this is by definition. You take the bracket of x and y, and as I have been using or in the whole time, I use curly brackets for my n. So this is the curly bracket of these two elements, plus L of x applied to y minus L of y applied to x, and then and now again, we define a dot on the vector space V, which is G and N as vector space via x dot y is L of x y, and then we can express what it means for this map to be a Lie morphism, the algebra morphism. So we see that this should be equal to this. So this means one, that xy minus xy square brackets minus curly brackets should be equal to x dot y minus y dot x. Secondly, I have the same thing as before. Yeah, so this applied to z should be this applied to z. So this is x dot y dot c minus y dot x dot c. And so we get these two conditions. And of course, I should not forget that all of these x's are derivations of n. So I do have to end up inside the derivations. So I do get the third property, namely L of x is a derivation. So if I apply x to yz, this should be equal to x dot y z plus y x dot z. And these three conditions are now exactly the three defining conditions for post Lie algebra structure on the pair Gn. Yeah. So this is post Lie algebra structure on the pair Gn. So as a conclusion, yeah, we do have such a semi-transitive affine action. If we do have such a semi-transitive affine action, we must have a post Lie algebra structure on this pair. Yeah. For the moment, I have been unable to also really prove the converse, but nevertheless, I was able to prove what I wanted to prove. Yeah. Namely, in this situation, we can formulate a more or less positive answer to Benoit's question. So this is a kind of theorem that I proved, I think, in 2003. Let me have a look. Yes, I proved this in 2003, and somehow a totally alternative proof was given by Oliver Bowers in 2004. And it says the following: the G be connected simply connected solvable Lie group, then there exists such a nilpotent Lie group, and is simply transitive by action. Go from this G to affine group. Or said differently, if you have a solvable Lie algebra G, then there exists a nilpotent Lie algebra N on the same underlying vector space, such that the pair Gn admits a post Lie algebra structure. This is exactly an analogous theorem. Okay, I will not go further into this. Yeah, but at least you see that in this geometric setting of affine actions on the Lie groups, you pop up with the notion of a post Lie algebra structure really more or less in a natural way. And actually, this also leads me to formulate an alternative definition for a post Lie algebra structure, namely the following definition, let's say lemma. Let Gn be a pair of Lie algebras and dot be a bilinear product. Linear product on the underlying vector space. Then this dot is a post Lie structure, a post Lie algebra structure. Structure on this pair, if and only if two conditions are satisfied, namely L of x is always a derivation, so I mean the left multiplication of any x is derivation of n, and secondly, the map from G to n summarizes the derivations of n mapping x to x comma L of x is a Lie algebra morphism. Indeed, I have shown that from this, I have shown that if you have this derivation, this exactly means condition 3, and this being a Lie algebra morphism exactly corresponds to those two conditions, because this was really my computation that I did over here. So having a post Lie structure on a pair of Lie algebras is just saying that you have a map of this form, where L of x is a derivation for all x, such that this is a Lie algebra morphism. And so actually injective Lie algebra morphism. And in my opinion, this is also a very useful way to think about these post Lie structures. So some of the results that I will prove in my in the next course, so we will be using this interpretation of a Lie algebra, a post Lie algebra structure. Okay, and now what are we going to do? So you can forget about everything about geometry. So I will not come back to this notion anymore, but I did want to give you this background. And now I will go back to algebras again. And so, as the fourth part of my course, I will talk about existence or not of post Lie algebra structures on pairs Gn, and this depending on their algebraic properties. Okay, this is a long title. So what I will do is I will consider 6 algebraic properties. The first one I have already more or less used, the property abelian. So if you have a Lie algebra, we always talk about Lie algebra G. Yeah, then of course, being abelian means that xy equals 0. Yeah. The second property that I will consider is the property of being nilpotent. Yeah, and I guess most of you will also know what it means, so you can define the series, the gammas, which are just, yeah, and then gamma I plus 1. So G is, well, it doesn't matter how I write it. Take the brackets of G with the previous one. Yeah, if this goes to 0 for a certain element, so gamma C plus 1 is 0, then we say that G is nilpotent of class less than or equal to C, and then this is the first one for which we get 0, it's really nilpotent of class C, or C star nilpotent. Then the third condition that I will use is the condition of solvable. I guess this is also quite well known, so you look at let's say G1, which is GG, and then GI plus 1 is the bracket of GI with GI, so not G with GI, but 2 times the same. If this tends to 0, yeah, so if G of D is 0, then we say it's, excuse me, it's D-step solvable. Okay, the fourth condition that I will be using what you should certainly know is that of a simple algebra. So this is a non-abelian algebra having only trivial ideals. Yeah. So for example, typical example is ln, let's say C, if we work over the complex numbers. Then I will also use semisimple algebras. Yeah. These are direct sums of simple algebras. And then the last kind of the algebras that I will be using are reductive algebras. You can write them as A plus direct sum of the algebras, say the simple part, and an abelian part. And so this is the reductive one. And the typical example you should keep in mind over here is G and C, which you can write as C plus S and C, where the C stands for the diagonal matrices. So all entries the same on the diagonal. So the scalar matrices. So the C elements are the form lambda, lambda, 0, 0. Okay, so this is what I'm going to use. Yeah? And then one more thing you should know for the rest of my talks is that in general, a general Lie algebra, take any Lie algebra, and I will be working from now onwards, let's say over the complex field, although most of the things I'm going to say are valid over any field of characteristic 0, but to keep safe, there from now onwards I work with field of the complex numbers. So if you have any Lie algebra, then it has a radical, which is the largest solvable ideal. Yeah, and then let me write this as R, and then you can write G always as an internal summary product of its radical and a semisimple part. And this I will be using also at certain moments during my talks. And now, what is the idea? So as I said yesterday, so I will use these notions and I have put them in my scheme over here. Now, when I write nilpotent, I mean nilpotent but non-abelian. When I write solvable, like here, I mean solvable but not nilpotent. So any nilpotent one is also solvable, but when I'm talking about the solvable one, I mean the solvable one which is not nilpotent. Yeah, the simple one is just a simple one. A semi-simple one, which is not simple. So at least two simple factors. And also here, a reductive one, which is not semi-simple. So if I use this word, I mean, yeah, not one in the category before. Okay. And the aim is now to fill up my scheme in a certain way, and I will put check marks in green or in red, whether or not there exists a Post Lie structure on such a pair Gn. Now, the ideas, so I'm looking at Gn, and this one satisfies property 1, and this satisfies property 2. Yeah? And the moment that I mark a green V, then I mean that there is an example of a G with property P1 and an N with property P2 such that the pair Gn admits a Post Lie algebra structure. Okay. In case I will indicate a red cross, I will mean that for any G with property P1 and any N with property P2, there is no structure on the pair Gn. Okay. So a green V means there are examples, the red cross will mean there are no examples. And maybe let me start and finish with the first part of my scheme. As I told you yesterday, if you take any Lie algebra N and you define the product that this equals 0 for all x and y, then you get a Post Lie structure on the pair N. Yeah. So you have that xy minus should be the product of x and y minus yx should be 0, so the brackets should be the same. Okay. And the two other properties are also satisfied. Okay. So if you have a zero product, then you have a Post Lie algebra structure of the pair N. So as a conclusion, this means that the first part of my scheme can already be filled up. Choose any abelian Lie algebra and the same. We have the trivial product, so I can put green V's over here. This exists. Of course, we can also find examples of an N and a G, which are both nilpotent and not the same, yeah, and also allow Post Lie structure. So this is not the only example in many cases, yeah, but at least one such an example. Okay, so I think I have to stop here. So tomorrow I will start filling up the whole table and study all kinds of properties of Lie algebras in connection with this Post Lie structures. So I do thank you for your attention today.
Oh, well, let's see if there are some questions. I saw that there were two questions in chat, but I think the participant is not online.
I can never read the chat.
Yeah. But can you read it now?
Yeah, I can read it now. I don't know the definition of sharply transitive action, but I guess this is the same. Yeah.
Yeah, just answer the question, because
yes,
maybe the participant will see it.
The question was, is the definition of simply transitive action the same as the definition of sharply transitive action? And I guess this is true, but I'm not sure because I'm not too familiar with the notion of sharply transitive.
Okay, thank you. Even though the participant is offline, maybe he will watch this after in the recording. So is there any other question? No, no, I think there is no
I
other
have
question.
Yeah,
Prince.
so is there an analog theory of Post Lie algebra, for example, in the sense of a correspondence between Lie group and Lie algebra? So Post Lie group, is there an analog theory in this sense?
okay, that's a good question. And to be honest, I did not really think about this, because the notion of left symmetric structure, you can really define it on Lie groups, and you use affine connections for this. So if you know differential geometry, the notion of a left symmetric structure you can really define on the Lie group level by using left invariant connections. A little bit is the same for Post Lie structures, but it's getting more complicated, and I have not seen people using it. But so I should think deeply if it's easy to translate to the Lie group level. But certainly there has not been really somebody studying this, in my opinion.
Thank you.
Thank you, Prince. Other question? Well, let's thank Karel again.